Molecular hydrogen, H2, also known as dihydrogen or hydrogen gas, was long regarded as being inactive and non-functional in mammalian cells. This was attributed to the absence of functional hydrogenase genes in mammalian cells. It was subsequently found that H2 exhibits antioxidant effects, protects the cells against oxidative stress, has anti-inflammatory, anti-allergic, and anti-apoptotic functions. Molecular hydrogen was also found to regulate cell death and autophagy, and stimulate energy metabolism. Molecular hydrogen does not readily react with most biomolecules without a catalyst. To initiate any event, H2 may react directly with strong oxidants, such as hydroxyl radicals, OH, in vivo. This review article focuses on the molecular mechanisms by which H2 performs multiple functions, induced via direct targeting or subsequent pathways, highlighting the direct reactions with OH, and interventions in free radical chain reactions to modify oxidized phospholipids. The possibility of structural changes in proteins that could be brought about by H2 via direct changes in hydrate water is also discussed in this article. The hydroxyl radicals, OH, are said to have a physiological role because they trigger a free radical chain reaction and may be involved in the regulation of Ca2+ or mitochondrial ATP-dependent K+ channeling. The mitochondrial ATP-dependent K+ channel, along with other important functions, also plays a homeostatic role in blood glycemic regulation. In the subsequent pathway, H2 suppressed a free radical chain reaction, leading to decreases in lipid peroxide and its end products, including 4-hydroxy-2-nonenal, 4-HNE. Derived from the peroxides, 4-HNE functions as a mediator that up-regulates multiple functional peroxisome proliferator activated receptor gamma co-activator 1-alpha, PGC1-alpha. As the other direct target in vitro and in vivo, H2 intervenes in the free radical chain reaction to modify oxidized phospholipids, which may act as an antagonist of Ca2+ channels. The resulting suppression of Ca2+ signaling inactivates multiple functional nuclear factor of activated T cells, NFAT, and CAMP response element binding protein, CREB, transcription factors, which may explain H2 multifunctionality. Inactivation of NFAT by H2 may also play a beneficial role in treating COVID-19, Alzheimer's disease, and advanced cancer. The possible role of H2 in lipopolysaccharide signaling, mitogen-activated protein kinase, MAPK, and nuclear factor kappa light chain enhancer of activated B cells, NF-kappa B, pathways, and the nuclear factor erythroid 2-related factor 2, NRF2, paradox have also been discussed here. A novel concept has been introduced at the end of the article discussing the possibility of H2 involvement in structural changes in proteins by initiating local changes in the hydrophobic interfaces of protein molecules, thereby providing an explanation to the direct targeting of H2.